Thank you, Mr. Chairman. Good afternoon, ladies and gentlemen. My name is Iztok Sustersic. I've tried to spell it out for you here. It's a little perhaps easier. However, whoever gets this right in the first go definitely deserves a beer. So my background is actually civil engineering. For the last 10 years, I was employed in both a structural design company and at the university as well. Recently, I've changed to a more academic role. I'm now the group leader of sustainable design with renewable materials at the InnoRenew Renewable Materials and Healthy Environments Research and Innovation Center of Excellence, so InnoRenew, COE for short. So without further ado, I would actually start with my lecture. Okay. And I'll actually start with quite a bold claim. So I think that Xlam needs to change at least a bit. I think it needs to be optimized, and I actually think it needs to be rationalized. So saying something like that about a material that was perhaps not solely responsible for this almost timber renaissance we've been seeing for the last decade or so is quite daring. Bear with me, I'll try to explain where I'm coming from. We perhaps should go back first, at the beginning where Xlam actually started, which is now almost 25 years ago, basically in the mid-1990s, sort of as a joint research between the Austrian industry and academia. At that time, timber in Europe was a lot cheaper than it is now. It was more available. And the beginnings were a bit slow, but then in the beginning of, let's say, the new millennia, the whole thing took off quite a lot. And if we look, let's say, just at the latest numbers in Europe, we're seeing that just the European producers are probably going to be hitting the 1 million cubic meter mark either this year or next year. So that's a lot of timber. That's a lot of trees also. And the reason why perhaps CLT took off so much, let's say like 15 years ago or so, was because it allowed us to build in height. Perhaps this building was the most prominent one in that perspective, so the first 8-story CLT building in the world, in London. And then after that, they just started sprouting all across Europe and the world for that matter. So 9 stories, 10 stories, that's hardly even gets to the news these days. So you also have the 17-story one in Vancouver in Canada, the Brock Commons, and the 24-story one is being built, so that's the Hoho building in Vienna right now. I'm slightly cheating with these two because they are hybrids. So they have concrete cores, which take the lateral load. But nevertheless, they have quite a lot of CLT within the structure itself. So it's not only that we can build high with CLT, we can also use it for the inner panels. We have a nice, healthy, warm building climate. We can also use it for smaller applications, but for some more, let's say, interesting architecture, for structural upgrades on seismically active areas, because it's so light in mass, but stiff on the other side, for cantilevers, for all sorts of things. So coming back to my original question, or my original bold claim, why should we rationalize Xlam? Well, a metal always has two sides, so we also have to look at the other part. There was a very prominent study made by Johnson and others in 2011, which outcomes were, in the end, that we will have more of the low-quality timber in the future. We'll be using more plantation wood, and that we may actually see spruce start to run out in as soon as 2020. Now, the last one is a bit of an overkill, so we still have some spruce, but we are definitely logging a little bit more than we should. So it's not only what we're doing in the forest, it's also what's happening in the nature itself. So, for example, a case from Slovenia, the country, it's actually the 3rd most forest-covered country in Europe, right after Finland and Sweden. That's also the country where I come from, and for that matter, also where your first lady comes from. But putting that aside, 4 years ago, we had one of the worst cases of sleet probably ever. And that resulted in this, and that consequently ended in this, the worst case of bark beetle damage in the last 30 years or so. Putting that into numbers, we've lost about 60% of our yearly logging realization for the last 3 years straight. I don't have the data for 2017. The word is it's even larger than it was for 2016. So in addition, it's also the timber stock that's changing. This is a case from Germany. So right now in Germany, we have 70% of softwoods and 30% of hardwoods. But the young trees are quite the opposite. We have 30% of softwoods and 70% of hardwoods in the young trees. The same case also then results in the prices of timber. So this is the price of spruce and pine for the last 15 years or so, and this is the price of beech, which is actually declining. So, taking from this, we may actually see quite a lot of hardwood being used in the future. But when I say that crosslam should be rationalized, I don't just mean we should just change a species from, from spruce to beech. I think that crosslam is a bit overweight, and I think it actually needs to go on a diet. So the question is, what happens if you go on a diet? Not the upper part, quite the opposite happens in that department, but you can see your ribs. So the trick question is, what happens if crosslam goes on a diet? Yes, it too starts to show ribs. So the thing is, when we were, let's say, trying to come up with this new element, we tried to combine the low material consumption of stick frame on one hand with the robustness, fire safety, seismic safety, versatility, strength, stiffness, etc. of crosslam on the other hand into this one optimal construction element without increasing its price. And how to do that? First of all, we had to keep the production cost the same. And second of all, we wanted to use the same materials as for regular crosslam, so basic, simple lamellas. Because these cases, this was done before and this is being done now. So taking a CLT slab, combining it with a Xlam or LVL, whatever rib, this is nothing new. But the problem is you have to make one, you have to make the other. These are usually not made in the same factory. You have to bring them together. You need labor, manpower, transport, etc. So this was out of the question. And second of all, these elements are more useful for larger spans. So let's say 10 meters or more. So that would be what, roughly 35 feet or more. And we were aiming for the, let's say, 6-meter spans. So again, roughly about 20 feet or so, where crosslam is actually quite optimal. If you go beyond 6 meters, you can do it without a problem. The thing is, if you want to fulfill all the serviceability limit states, you're getting quite thick plates and you're not being as rational as before. So sticking with the 6 meters, perhaps trying to push it a little further, maybe towards 8 meters or so. And first of all was to develop this one-step production procedure. So how to incorporate the ribs into the main CLT structure. Well, we did this by actually using a two-sided pressure. So from the sides and from the vertical direction, and in the end you get this very stiff, very robust connection, even if you have very slender and thin lamellas. Second of all, it was the use of standard lamellas. You can imagine if they're very long, they're very slender, they can get a little crooked. So if you have this side pressure, you can actually straighten them up and get this very compact and robust structure in the end. So of course we had to put our money where our mouth was, and we made this testing metrics. So altogether, when you combine the cross sections, variations, lengths, and so on, this was about 39 specimens altogether. So these were meant for bending. This was then meant to be as a wall for buckling, and we made them on a Ledinic cross press. So this is a press that's actually already on the market. It's a modular press. The main thing is that it actually allows pressing from 3 sides already. So the main vertical pressure, but then you also get the side pressure and longitudinal pressure as well. The problem is that, all the presses are usually custom made. So they're not like lying exactly in the backyards of producers. So we were really fortunate enough that Ledinic had one of the segments, not exactly lying in the backyard, but they had one. And they were also kind enough to modify it for us. So we were able to make specimens up to 4 meters in length and up to 1.5 meters wide. And so we started with all the procedures. So like I said, basic lamellas. First of all, you had to regrade them all, measure all the properties to get the correct modulus of elasticity. So we knew for each and every lamella its properties. This was very important for later finite element modeling. So after doing that, so we had a couple of rejects, but the rest of the lamellas were sort of classified into 3 different classes. So the stiffest ones, the medium ones, and the most flexible ones. And we tried to actually spread the properties across all the final samples, so we had as uniform samples as possible. So these were little bundles. You can see there, let's say the bottom side of the compression plate. You have the ribs, the flat lamellas, and these are the so-called, let's say, dummy elements that ensure that the vertical pressure also reaches the flat-lying lamellas and not only the ribs. We were using polyurethane for gluing. This is pretty much standard in Europe. And then we put our little packages into the press, pressing them from the top, from the side, and then they started coming out in all different shapes, sizes, according to the matrix I was showing you before. So this is this very, very stiff, very robust joint. So even if I have like a very super slender lamella, even if it's like an OSB plate or whatever, this is a lot easier to put together and to actually then have a stable connection. Because if you try to glue on a very slender and narrow lamella directly on the CLT plate, it's going to give you, at least some gray hair, if nothing else. So we started with the testing later on, standard 4-point bending testing. And the interesting part was, this was actually, let's say, better than we expected, was that we did not have any brittle failures. We basically had sequential, gradual failures of individual elements. So you have different failure modes here, from like really exact proper shear to combination of tension of the ribs and all various other possibilities. If you look at the displacement force diagram, you see this. So basically what happens, the load starts to increase, then one of the ribs breaks, the load is then redistributed to the other two, then starts to increase again, the second rib fails, and then again the redistribution and so on. So basically in the end you have this zigzag pattern of the load displacement curve, and basically you almost have a sort of a ductile post-critical behavior. This is very uncommon for timber structures in general. Xlam beams, whatever, massive timber. When you stress them, they usually fail pretty much, in one go without any sort of ductility. So brittle failure. This was quite the opposite in this case. One thing we also found out was that there was no distinct shear lag effect. Whenever you have sort of a rib-type plate or any T-shaped section, you always have this presence of the shear lag. Now, in our case, the ribs are actually so close together that there is no such shear lag present. There was a difference in the measurement of strains on the top of the compression plate. However, this was more or less correlated to the different stiffnesses of the ribs we were actually intentionally putting there. So there is no shear lag effect, which in turn means that we can actually use the complete cross-section without any reductions. We can use the full potential of the material. Okay, coming to walls. This wall specimen was 2.95 meters tall, which is quite standard for Europe because this is the limit for our standard transport, so we don't have to use some special lorries. 1.25 meters wide. This is the standard, let's say, width of OSB plates in Europe. And only the plate was supported, so the ribs only offered buckling stabilization. Now, speaking of ribs, whenever you're dealing with CLT construction, unless you have a contact facade, you usually end up with some sort of rib or rib-like elements because you need them to carry the substructure of the facade. In this case, you have to buy them separately. You have to bring them to the construction site, install them, etc., etc. In this case, they already come within the package itself. So, coming to testing, this very small specimen, which actually has 30% less of timber than a standard 10 centimeter CLT plate, which is the most common plate used for walls in Europe. This small sample could actually take 1,100 kilonewtons of force. So if you translate that into length meters, that's close to 100 metric tons on the length meter of wall. That's really a lot considering the whole, let's say, material ratio towards the force thing. So the ribs, in the end, this was the final state when they actually sort of ripped out of the structure. But the main thing was the whole thing was very controlled. It was a very controlled behavior without any sudden buckling, which is quite the opposite, for if you have any other type of let's say, wall or a column system. So putting some numbers together, so let's say the comparison of timber consumption for standard CLT plates compared to the ribbed variant. If we're talking about roof plates, where the governing criteria is either strength, but in most cases it's displacement, we can save up to 50% of timber compared to standard CLT, while still keeping the same performance. If we move to the to the floor plates, where the governing criteria is usually vibration, we can save up to 40% of timber compared to standard CLT. Coming to walls, we can save at least 30% of timber. However, this is just a numerical comparison. If we have a 35% higher load, we can still save 30% of timber. If we move to the, let's say, fire load case, this one is performing about 5 times better than standard CLT, because you're actually using the whole cross section and you have the massive side orientated towards the fire. So this was also quite good. And now coming to the production line. So all what I was explaining before is all pretty much in vain unless we can actually make these plates. This is, for example, a production line that Ledinec is making. This is their standard cross press. You can see that it's a very small part of the whole, the whole factory. So, from CNC machines, finger jointers, and so on. So this production press actually gets a whole new addition. This is where you actually make the rib plate. So you can have a combined production of making standard CLT combined with the ribbed CLT. The whole production is fully automatized. It has a capacity of 300,000 square meters per year. That's about 15% less, let's say, if we would translate that comparing to standard CLT. Nevertheless, we have quite thoroughly established that the production cost for the rib plates would remain pretty much the same as for standard CLT plates. Okay, summing it all up. If we have these rib plates, we keep all the benefits of conventional CLT. If we have this dedicated production line, we keep the production costs the same. For floor plates, we save up to 40% of timber compared to standard CLT, and for roof plates, we save up to 50%. We save at least 30% of timber for wall elements, which also have a higher load-bearing capacity, and they have a very huge potential for multi-story buildings. And since we have the ribs already incorporated in the main structure, we also save on the outer envelope building costs. So all the results that I presented so far are originating from the hybrid cross-laminated timber plates project, which was performed under the Wood Wisdom network, so one of the Horizon 2020 projects. I would like to thank all the partners that took part in this project. And before I completely finish, I have to make some additional, let's say, invitations. So InnoRenew is hiring. We have these open positions. We'll soon be having additional positions. So, if you care to join us in a very cozy country, in a nice new environment with nice people, already half of the employees are foreign. Actually, we have 6 or 7 Americans already. Please visit the website and apply for any positions you may be interested in. Thank you for your attention.
Thank you very much, Iztok. We do have some time for questions. Are there any questions right now?
Yeah, Michael?
What sort of fire rating does it have?
I mean, you can, actually depends on how you turn it. If you actually turn it upside down, you can go to 60 or more. If the ribs are turned on the bottom side and you don't have any sort of plaster or whatever cladding, you can go up to 30 minutes. The good thing is if you actually turn it upside down and have the ribs sticking upside, is that you put on additional cladding and additional insulation, you get a very high fire rating, you get really good acoustic properties, and you also get some space left for installations. So I've dropped the slide out because I thought it was going to be a little too long, but yeah, I can show you that later if you want to see it. So.
Over in the middle there.
Did you do any lateral loading of the wall system?
No, actually not, because the lateral loading is usually more or less governed by the connections you're using, so even a 6 centimeter plate would more or less suffice for most of the cases. So.
Any other questions right here?
Did you look at allowable holes in any of the
You mean from?
surfaces?
Yeah, well, You are limited to a certain extent, so depends again how you turn the plate. If the ribs are, turned to the bottom side or to the upper side, but yeah, there is a limit to what you can actually put through. So unless you use some sort of strengthening, so.
Okay, I don't see any more questions, so thank you very much, Iztok.
Thank you.